Cool, that's recording. All right, so let's get started. Sorry about that. So I think last week where we left off, I think I didn't really cover two of the questions properly from week 4, the decision tree. So let's quickly cap those off. So there were two ones that I didn't talk about. It was this one, question 2. So they're essentially fitting a decision tree classifier to this data set, and the first thing they do is they calculate the information gain. Let me put that there. They calculate the information gain on, they're trying to work out, what to split on effectively, right? So they're splitting on species, this one, and rebel, and then just purely using the information gain, which is the formula of which is here. Information gain, and remember, information gain, you can think of it as the weighted average change, a decrease in impurity. So how much more pure it becomes, or how much less impure it becomes, right? So just purely based on that, we can see that it's 0.52 for species. So this guy's giving a 0.52 information gain, and then rebel, this field here, this predictor, is giving a 0.48. Information gain. So it's quite close. But one of the things to note is that information gain is biased towards features with more levels. So we can see here, species has a whole bunch, like say 5 levels, 5 different types, 5 unique values, whereas rebel has 2. So it's gonna, be biased towards this guy a bit, right? It's gonna give it a bit too much information gain. And so one of the ways we allow for that is to use the gain ratio. And so the gain ratio effectively is the original information gain, but then they scale it back by this factor which effectively says how impure this is, right? So the more impure this is, in other words, the more levels or the more unique values, it will scale down the information gain. So think of it as a penalty for having too many levels, because just the gain by itself, that will be biased, or that will prefer features such as species with more levels. So you plug into this formula, so you simply just go 0.52 divided by 2.46 divided by 2.46. Oh, there is a chat, isn't there? Okay. Yeah. So I just checked my email. Yeah. So okay. Yeah. So another way you could reach me, and feel free to test it out, is so in Microsoft Teams you should be able to see where would it be? Oh, okay, thanks for that, Evan. Team posts is all right chat. Okay, I guess I can. Okay, cool, fantastic. I'll just look here then. So if you post in general in this tutorial chat, then I should be able to see you, or you can send me an email, so I have them all open somewhere. Cool. So after penalizing for, I guess, the impurity or the number of levels in each of the features, then we see that it turns out that species has 0.21 versus gain ratio, which is 0.49. So this guy used to be better, at least from an information gain perspective. We would have chosen that. But then after we penalize it for having so many levels, then we're like, okay, let's go with the rebel. So that's this question is effectively just using this gain ratio concept. Okay, and I talked about this already. The other thing I missed was this guy here, question 4. So it's saying hypothetically in a multi-class learner. I can. That's okay. So I'm just replying to a student. Okay. Sorry. So recall, so a lot of the examples we've seen so far, they are binary classifiers. But binary is just 2 things: 1 or 0, a true, false, a healthy, unhealthy, dead, alive, etc., etc. But of course, we can actually do multi-class classifications, classification problems as well. So for example, if we're trying to classify species of fish, It might not just be salmon or sea bass, that example that's always in the lectures. It could be, I don't know, tuna or something, or well, whales aren't fish, but some other kind of fish, trout or something. So it's asking here, what's the worst case scenario in terms of error? Now, if you think about it, what's the way these trees split? I mean, you could, in theory, think of a tree that is wrong, like 100%, inaccurate, right? But that's not how we split these trees, right? So you recall that when we do the splits, the prediction is the mode or the most frequent, I suppose, a category within that bucket. So let's say you split the tree a few times, and then that leaf node where that prediction is, that's going to be the mode, right? So just based off that, you can't have a tree which is all wrong. It just won't work out that way. Now, the worst possible tree would be just like a stump, right? And without even any branches, just the root node, where the root node is the leaf. There's just that one bucket. This is not the worst, but this is the simplest possible decision tree. And and sometimes it has use. It could be possible that your data is so noisy that sometimes the best prediction you have is just the most popular, the mode, the most common class, or could be the average, in terms of regression. But for classification, it'll be the mode or the most common class. So, given that, and if in this example, all of the guys here are evenly distributed. So the worst possible scenario is you just have a stump, because if you add more splits, the classification error will get better, at least on the training set. But here we're just considering the training set. We're not talking about holdout, not talking about test. If you add extra branches, the error will improve, right? But the worst possible one is a stump. So in worst case scenario, you just choose one class. Let's say there's 3 classes, salmon, sea bass, and trout. You choose trout. Okay, for all of them, you predict trout for all of them. So then the error is going to be 2/3, right? 2/3 of the time it's wrong. So that's what it's saying here. Cool. All right, so that's the remainder of week 4, which I skipped out on last time. Now let's move on to today's lecture. So just a reminder, all the stuff from today. What's going on here? Just a reminder, all the stuff from today I've uploaded here. So if you go to Teams, General Files, it's all here. So I've got some slides for today. They're not as detailed as normal, but that is this guy here, as well as the solutions for today. So the kernel methods ones here and here. So feel free to download that, open it up, and look at it on the side if you like. Okay. So, what did we talk about? Oh, it's quite zoomed in. Yeah, so if you're wondering why it looks like this, it's because I've got Windows stacked on top of Mac OS here, because I hate the Mac OS Office. I think it's terrible. So then it just, which is why I've got the Windows on this side and Mac OS on this side. But anyways, so what happened last week? Let's give a quick overview. Okay. So we've done that. So margins and loss functions, right? So that's one of the first things. Okay, cool. So here we have a classification task with 2 predictors, x1 and x2. So you got your 2 features, and here's your basic linear classifier, which is also a perceptron, which we'll talk about later. And anything above the line is going to be blue, predicted to be the blue class. Anything below the line will be predicted to be the orange class. Now, the question is, how do we, we could have several lines, right? We could have, I don't have an easy way to draw on the screen, but, we could have, you could have a line, I'll draw on the screen. You could have a line that says, goes like this. You can imagine you can tilt this line, rotate around clockwise, anti-clockwise, right? Shift it up and down a little bit. There's actually quite a few, lines that we could choose, right? And they would all have the same, accuracy, right? Accuracy being the percentage of predicted values that you get correct, right? So you can imagine you could shift this line like a millimeter up, a millimeter down. You could rotate it, a couple of degrees clockwise, anti-clockwise, and it still have the same accuracy. So in this case, the accuracy, or 1 minus the accuracy, is 1, because you have an error here of, well, one of them is wrong. Then all those linear classifiers, whether you shift the line up, shift the line down, or rotate it slightly, will be the same. So the point of this is we're trying to say, okay, let's try and measure, something like accuracy maybe it's a bit too blunt. Let's try and be a bit more nuanced. Let's try and quantify or try and measure how good or bad a particular classifier is, given the same accuracy or the same number of let's say observations it predicted correctly and incorrectly. So that's where margins and loss functions come into play. So you might recall we've seen loss functions quite a bit. In regression land, we see it as quite commonly root mean square error, mean square error. There's some loss functions that you can use in classification. One quite common one is what's it called? Log loss. Where's Wikipedia? Yeah, log loss. So effectively, this works, for your classification. Where's the formula? Yeah, so this might look a little bit similar to your entropy formula, isn't it? But effectively, what it is let's say you have two classifiers, right? And let me pull up an example actually. Okay. Oh, and by the way, in Microsoft Teams, I believe you can zoom in and out. So if you hit Control or Command, depending on what operating system you're on, and scroll, I think you can zoom in and drag the screen. So if it's a bit hard to see. Okay. So let's say you have these are observations. Let's say Y and then Y hat. This is, let's say, model 1, and this is model, say, 2, right? And let's go here. Okay. Okay, so here's our data, and this is the actuals. These are the actuals. Let me just zoom in a bit more, just so you guys can see. Okay, so here's a toy example, and we've created some model. We've got a model 1, model 2, and it's binary classification 1 or 0. Now, and let's say the threshold here is if Y hat is greater than 0.5, then we say the prediction. Then we said we classify it as 1 and then 0 else 0. Yeah. So you can see here actually that I guess the classification is still the same. So all these guys here in both models, they're both classified as 1 or the positive class, and all these guys here, they're all classified as a negative class or 0. They're not positive class, right? But I'm sure you can all understand why we think this model. I'm sure you can appreciate why we would think this model is better than this model, right? Even though the classification is still the same, right? This guy is far more certain, right? This guy's all right. Look, we're really confident it's a 1, and it is a 1. And this one is like, oh, really confident it's a 0, and it is a 0. This model is kind of in the middle. It's not as sure, it's sort of on the fence. So things like your loss functions, so things like your log loss, will capture this effectively, right? Now I know there's things like the Gini coefficient and ROC AUC. They don't exactly measure this, although they might indirectly. But you don't have to worry about that. I think log loss is one of the more common ones. Classification metrics. So things like log loss will take this into account. Now the thing is, right, for both these cases, the accuracy is the same, because it's the same number of correct classifications in both ways. So that's effectively what Gellerer is talking. What Gellerer is going on about there. So we've seen a bunch of these ones. Metrics. We've seen the ROC. We've kind of talked about log loss. F-score we've seen somewhere. Accuracy we've seen. Precision recall, which is related to this, we've sort of seen. Okay. Back to the slides. Where are my slides? Here. Okay. Cool. So that's why we care about the loss function, because we want to know not just how accurate it is, how certain we are. Now, margin I'll talk about a bit later, but let's review this. This is your basic linear classifier, and effectively it's a discriminative algorithm because, again, revision, discriminative means you just model, the class given the features directly. You remember your generative, you use Basel, you flip it around, and then you model the prior. So the prior, the likelihood. Well, you model the distribution of your features given your class. I forget if it's called the prior. It's a prior likelihood, one of the above. But it's a probability of x, the feature, the vector x, the feature, given your class. So this is discriminative algorithm. Quite straightforward. You just get a line, and if you're wondering what this chap here is, effectively. How do I do this? I just do it. So this one here is just your W. I guess they roll up. W1, and then X1 plus W2 X2 plus ... plus W. And then xn plus your constant term. So this guy here, I can't even take a screenshot, can I? But well, hopefully you can see the screenshot. This guy here is equal to this guy here, and actually maybe I'll type it here. W. So let's see, W. Really need a vector, and then it's transpose. So this weight vector transposed multiplied by, So I mean, I know the lecture notes. Don't really. I think the alignment's a bit off, but you get the point. I know the lecture notes don't seem to like bolding or adding vector lines to it, but I like to have it in just I find it a bit clearer. So plus b. So this guy is effectively this guy, and if you want to know what this is it's just the hyperplane. This is a generalization of y equals mx plus b, right? That's a line, you have a plane, and then you have hyperplane when you get many more dimensions. Why is it American spelling? I hate American spelling. Okay. Anyways, cool. So that's what that guy is. And so if you plug it into this formula and it's greater than 0, then we'll classify it as a positive class. If you plug it into this formula and it's negative or 0, I guess it's threshold. You can define it either way you want. But if it's negative, then we classify it as the negative class. So that should be straightforward. I guess in the middle, it doesn't really matter. You can make a choice. You just toss a coin. You can make it 0 if it's on the line, positive, negative. It's a border case. I don't think it really matters. Cool. That's that guy. And of course the issue, as I was talking about before, is for the same given accuracy, there's many lines. So going back to this example I had in Excel, right? You can imagine like maybe model 1 could be like the line right in the middle. Maybe that's a really good one. Then you could have some like not so great model which is like a bit shady, the line's a bit off, but maybe it's got the same accuracy, right? So we want to quantify that, and there's a couple different ways. a couple of different ways. One is the loss function. The other is what we call a margin, which is related to the support vector machine, which we'll cover in a bit. Yep. Sorry. Okay. So the perceptron. The perceptron, it's something you'll come across later when we look at neural networks. But you can kind of think of it as so your basic linear classifier is a perceptron. A perceptron is like what you think of as one neuron. So when we look at the neural networks later, it's a network, a whole bunch of neurons, right? Again, don't worry about this. We'll look at it a bit later. But effectively, each one of these perceptrons is one of these chaps here, right? So again, we'll look at it a bit later. But just keep that in the back of your mind. That's why they call it a perceptron. The perceptron is that, think of it as a neuron within a neural network. And of course, this is linear, but when you combine it up with all your hidden layers and everything, and you put a network, then you can model, not basically anything, but you can model many things and non-linear things as well. Cool. Yeah. So this is again that classification rule that I've been harping on about. So all this is saying is you plug it into here. If it's greater than if it's positive, let me. Can I? Yeah. So this guy here is just this rule basically. Okay. What else is important? Perceptron learning. Okay, yep. So perceptron is basically a linear classifier, and it is the building block of your neural networks. Now, perceptron learning. Let's focus on this algorithm. Yeah. So essentially, what it does is you have all your weights. So maybe where did he go? This one. Yeah, so you initialize all your weights to 0. Like in practice, it's they typically use a small random 0 value because it's easier to converge. But in this case, a simplified algorithm, we set this all to 0, and we go through while we haven't converged. Ignore this converge for the time being, and this steps through the entire data set. So for every single data point, okay, we'll start here. Then this one, then this one. Oh, it might not be in order, but say this one, and this one, and this one, and this one, and this one. So it steps through all the data points. And this guy here is saying, okay, if it's misclassified, then we do something. Because you can imagine, right? Like, if for some reason you set all the weights to 0 and everything's perfect, you're done. You don't need to do anything else. You're good, right? But here it's saying if it's misclassified. Now, why is this misclassified? Now, remember, our prediction is this guy here. Actually, I have it here. Yep. So this actually relates to the first tutorial question. So maybe I'll just blow this up a little bit. Yeah. So if it's misclassified, this and this will be negative. Why? Because think about it. Let's say the y is actually positive, then this is positive. Now your prediction. This is your prediction, isn't it? Oops. Well, w dot x or w, so then I should probably clean up the notation, but okay, this is a vector. Ah, crap. Maybe I just bold it. I'll be lazy. Okay, bold means vector because I'm lazy. So transpose. I'll just do a dot. Where is my dot? Okay, cool. So remember, this guy's our prediction. So you saw before as W transpose X, but it's the same as dot product, same thing. Basically, you're multiplying your weights with each of the features. So weight 1 times feature 1 plus weight 2 times feature 2, dot product. So this is your prediction. Now remember, if we predict positive, this will be positive. If our prediction is negative, this will be negative. So if it's correct, this will be positive, and this will be positive. So therefore, if it's incorrect, this will be negative. Okay, so this is saying if our prediction is negative, then we want to do something. Then we want to bump the weights, right? So we'll go, okay, again, so this is a vector, this is a vector, the W is a vector here. So if it's incorrect, what we do is we nudge the weights. So now you can imagine, right? Let's say it's a positive class and we goofed up, we stuffed up, it's wrong. So what do we want to do to the weights? Well, we want to nudge it up, don't we? Because it was too little before. Because if it was incorrect, if it was meant to be positive, but we classified it as negative, it means that the weights were too small. It was too small. We want to make it bigger, right? So we push it up by a little bit. So we go plus, and again, we stuffed up. It's meant to be positive, so positive x. So we push it up a bit. And of course, it would be the opposite effect if it was negative and we misclassified it, right? And this here says, okay, converged. We assign it to false. Now, in this case, convergence means that we don't have to make any more nudges. We don't make any more changes. So if we run through the entire data set and it's perfect, everything's classified perfectly, we've converged, we're good. Of course, you can imagine the problems here because you could have you could never converge. This could be an infinite loop if it's not perfectly linearly separable. Now I'll go through that. I'll talk about that a bit more. But perfectly linearly separable means. So this is perfectly linearly separable. This means that you can find a line or a hyperplane in more dimensions that can perfectly separate your data into your two classes. So here's perfectly linearly separable. This exclusive or XOR is not perfectly linearly separable because you can't draw a line which is perfect. It's just you're always going to stuff something up. Okay, so that's this algorithm here. I should probably speed up a little bit. I'm going a bit too slowly as usual. Okay, so that's that algorithm. Some problems with it. Blah blah blah. Okay, there's a concept called duality that is talked about quite a bit. So duality just means that if we have an optimization problem, can we express that problem as something else that's simpler and optimize that instead? So I think it's more relevant for the support vector machines, but they apply it here to your perceptron classifier or your basic linear classifier. So I think actually that's the first tutorial question. I'm going to segue out here. Yeah. So So basically, the first tutorial question is asking us to. They want us to compare. They want us to compare. This is the basic perceptron training algorithm, and then this is the dual form. Okay, and they're saying, okay, well, how they're related, what's happening. This I hope we all kind of get. We're just going through the data set, and if we misclassify, then we nudge the weights up or down depending what we need to do, right? Now, how does it relate here? So, everything's kind of the same. The only thing which is this guy in the middle here. Now, the difference here is that you can see here instead of that W, X, they have this summation, not ugly, but this summation guy here, right? So, but what is the W? The W, is the weight vector originally is the cumulative nudges and bumps, so far to date, right? So you can imagine here it starts off as zero vector, right? And then you go through the data set and you bump it up and down, depending on all your misclassifications. That's effectively here. So you start, this alpha tells you whether you need a bump or nudge or not, right? So effectively you go through here and, at first this is all going to be 0 because, all your alpha i's are set to 0, which is the same as this guy. And then so so initially it's the same as your weight vector being set to 0. Now if it's false, then you say, okay, let's do a nudge. So this is like a indicator variable. You can think of it as a flag. It's say, okay, let's nudge, right? And so it's the same as here, right? Here, every time you make a mistake at a particular observation, let's say observation I is equal to 1, you make a mistake. Okay, cool. then we're going to nudge the weight vector, with the first observation. Now, same thing here. So let's say you go through observation 1, you make a mistake. Okay, all right, cool. Then I'm going to nudge AI, which is telling alpha I, which is telling me that how many times I need to nudge the first observation. I increment it. I add 1. So hopefully you can see how they're related. So here is this guy is basically W, except it's expressed as the cumulative nudges. Okay. Yeah. So that's what this guy's saying. The question 1 is essentially asking you to compare the standard Perceptron training algorithm with the dual form, which is I suppose it's another way of expressing it, which is meant to be easier to compute. Cool. I'm just gonna check my emails. I don't think anyone's sent me any messages. Let me check team chat. I don't think anyone's sent me anything, so it's okay. I can keep going. Right, what's next? Cool. Yes, fine. We can talk about support vector machines. This is the meat and potatoes of last week's lectures. We'll talk about this a bit later. The kernel trick. Let's go support vector machine. All right, cool. Support vector machine. Support vector machines are known as strong learners. Strong learners. That's just something which is quite powerful right off the bat. So this contrasts to a weak learner. A weak learner is something like a decision tree stump, maybe a decision tree of only 2 branches, or maybe less than 5 branches, say. Can often be quite good right out of the box. The support vector machine. Of course, yeah. But yeah, let's go through a few different variations of our support vector machine. But in a nutshell, what I want you to understand is the support vector machine. How it works is it finds the best separating line or hyperplane. So it's effectively doing this. It is doing this. Actually, let me get the perfectly separable one and find it. A support vector machine does this, right? It finds a line or a hyperplane in more dimensions that separates your data. Now, there's a few differences to your Perceptron, which we'll go about in a bit. But just think of it as the best separating line, okay? And it relies on linear separability until we learn about the kernel stuff later on. What do we go up to? Keep bumping around. Is it this guy? Yeah, I think it's this guy. Cool. Yeah. Okay. Cool. Right. So again, yeah. So it goes back to our question before. How do we find the better classifier? I think I already hinted at a few of them. One was the loss function, but actually that relies on us having a probability prediction, right? There's something which the support vector machine uses to sort of quantify which one is the best separating hyperplane or line in this case. Hopefully you can see why you might. I mean, it's a bit subjective, but hopefully you can all agree that the one in the middle. Actually, which is better? Yeah, maybe the one in the middle. I mean, I'm sure we'll all agree that this one's not great. I mean, it feels like this is better, but let's focus on why do we think that the middle one is better? How do we? I mean, like, as humans, we can look at it and go, okay, cool, that one feels like it's going to be the better classifier, but machines can't really feel, yes. So we need some way to quantify it, that feeling that the one in the middle is better. Enter your margin. So here it is. So margin effectively is, think of it as, I think I saw it, I don't know if it was in, there's a really great resource which I highly recommend. There's some legends in machine learning, Trib Sharani, Trevor Hasty, and those guys. Where did I put it? I think it's somewhere here. Okay. Did I put it here? this one. Yeah. So this book I cannot say enough good things about. The good thing is this guy here is what's going on? It's freely available. Okay, this is not good. I think it's previewed. Let's open up in. Okay, cool, we're back. Yep. So I can't say enough good things about this. Unfortunately, Trevor Hastie's passed away, but he's actually written quite a few packages in R. Like there's the elastic net regression in R, which I believe this guy wrote. But these are a bunch of Stanford professors. They're legends in the field. I highly recommend this book. I think it's one of the more famous machine learning textbooks. Yeah, look, it is in R, but I mean, at least I don't mind R. I mean, I think a lot of people in computer science pay it out, but in my opinion, it's better for stats. I mean, Python is probably better for machine learning, but you know, the statistical packages in R are quite good. Anyways, like, I mean, you don't need to look at the programming. They talk about a lot of the maths. The focus really is on the maths here. Anyways, I highly recommend this book. Actually, I might even just dump it in the in our group here, because this is a great read. Honestly, I think it's fantastic. There's actually a more advanced one called Elements of Statistical Learning, but that's a bit of a hard read. I mean, feel free, but I would start with this. Let me just put it here. I think the space. So I just upload it to the file, so you can download it there. Anyways, it's freely available, so I don't think I'm breaking any copyright laws. You can just Google it, and they made it like they've basically open sourced the book, kind of. Cool. Anyways, so the reason I bring this up is the analogy I think they use is that this is kind of like a road, you know. Think of it as a street between, you know, two sets of houses, right? And the margin, you can think of it as how wide the road is, you know. So here you got like a bunch of houses. You have this road in the middle, and the margin is from that red line out to the end, right? It's the it's the width of the road. Okay. So what do we notice? The one that we thought was the best, this guy in the middle, has the widest road, the widest margin. Now notice here that this cannot allow for, like, if there was a blue dot here, it would be stuffed. This current, what I'm talking about now, only works for perfectly linearly separable data. So you have the blue houses here and the orange houses here. If you had a blue house here, it wouldn't work. Notice that all the blue houses have to be on one side and all the orange houses have to be on another side. This might sound like a crap algorithm, but we'll talk a bit later about how we improve it. But this is just the basics, right? And so what they call this is called a hard margin classifier. Now here we go. Here's a support vector machine. It's Wikipedia, so super official. Hard margin classifier, right? So it has to be perfectly linearly separable, right? Later on, we'll talk about soft margin, which allows for errors, you know, allows for misclassification. But for now, we start with the hard margin. Cool. So I think we agree that, you know, we want to maximize the size of the road, the size of the margin. Okay. Yep, so we want to maximize the size of the margin. And what do we notice as well? Why is this called a support vector machine? Now, it's called support vector because, do you see these circled guys here? Those are the support vectors. Think of it as supporting the, maybe even just think of it as supporting the road, you know? This weight vector, or this road, is entirely defined by those 3 points. So what I mean to say is, you know, you could add like a if you add any minuses anywhere down here, it doesn't matter. It won't change the support vector machine one bit. Likewise, if I add a plus sign anywhere here, it won't change the classifier one bit. This weight vector, and hence this support vector machine, only depends on these 3 guys here, the support vectors. That's why it's called SVM, by the way. Now, there's a whole bunch of maths here. Now, I think the important thing to keep in mind here is, effectively, what we're trying to do is we're trying to solve for W. This weight vector, which is the gradient of this line, and there's a mathematical concept or something. The gradient is always perpendicular to a line. So this line here, that gradient is perpendicular, this W. So let's take a step back. What we're trying to do is we have this data point, this data here, the plus signs and the minus signs. We have some hyperplane. Wx is equal to t. This is a linear equation. This is a hyperplane. We want to find the best W and the best T. Now, what is best? We define best as the fattest road, the widest road, right? So just keep in mind, this is what we're trying to do. We're trying to optimize the margin size by changing W, by changing T. Okay. Yeah. So I'll need you to go through the maths. It's quite involved, honestly. But long story short, they simplify everything into this guy. So effectively, your optimization problem went from here, using a few geometric results, it turns into maximizing this subject to this. Now, the problem is this is not good to optimize. And now this is where that concept of that duality comes in. We're like, okay, this is hard to optimize. How can we improve this? Enter your Lagrangian multiply. So your Lagrangian yeah. So it's a way of finding. It's a way of optimization. So here's one form of it. We want to maximize something subject to some constraint, and we can turn into this. And then we can find the stationary points and solve for that, and those are our optima. Yeah. So if you're wondering about this, I think actually Khan Academy has a pretty good explanation. Like if you're curious about this, I mean, I think this is a pretty good explanation of the Lagrangian multipliers. It's not needed for this course, but if you are curious, I think this one's quite a good explanation. Anyways. So we use we start off with our problem, which was effectively we want to find the best W and T such that we maximize the margin. Using some geometric results, we can turn it into this. This is hard to solve, so we use Lagrangian to then convert it into deriving. Where's the final form? Yes, then we find that we can end up with this guy here. Now, a few things you note is that this, in terms of the features, we only care about the dot product. Now, this will come in handy later. Keep that in the back of your mind. This only depends on the dot product of the features. This will come in handy later when we talk about our kernel functions. And we can also express this as, alternatively, we can express it like this, because with the weight vector here, it will be 0. So the alpha tells us, if it's a support vector, right? Now, alpha is going to be 0 if it's not a support vector. So we can also express the weight in terms of just this expression here, the support vectors. Okay. So the steps to do this are, we get the data, okay, and we put this data set into Lagrangian, the optimization problem. Then we solve for the stationary points to find the optima. I mean, I forget if it's maximization, minimization. They keep flipping around with the signs, but whatever. We solve the optimization problem, and that will give us the best weights. That'll give us the best W vector and T, which will give us this line here. And then once we have that line here, we can just use it like any other linear classifier. We can, we can chuck it into here. We can put it after we solve for W and T. I mean, you can think of this as T really. We can plug it into here, or it might be negative T. I mean, you can flip the sign, doesn't matter. But anyways, once we solve for this, the best W vector W and the T, we can plug it in here, and then this will give us a classifier. If this is greater than 0, then it's positive. If it's less than 0, then it's negative, etc., etc. Okay. Now, there's actually something else which I don't know why I don't think it's covered here, oddly enough. Might be next lesson. Oh, here it is. Okay, here. Margin. Like, cool. So, you might recall I mentioned a few different types of SVM. So there was the hard margin, which is what we've been talking about today, is hard margin. Up to now, is the hard margin classifier, which means that it has to be perfectly linearly separable. We cannot make a mistake. Obviously, you can imagine this creates a problem in real life data because many things you're not going to be able to find a line or a hyperplane which can perfectly separate the data. Now, your soft margin classifier, think of it as it's effectively the same as your hard margin classifier, except now there's a budget. Think of it as there's an allowance for error. There's allowance for error. Let's see the form. Yeah, here we go. Yeah, so the noise. Yep. So, yeah. So here you can see here, this data is not perfectly linearly separable. There's a mistake here, there that we just can't avoid, right? So this is our slack variable or our budget for error, and this becomes a hyperparameter that you tune later on if you're fitting it. Okay. So now optimization problem becomes this. We have this budget. So this is the error of each term. And this is like our allowance or penalty for error. Now obviously, the higher the C is, the more you penalize error, which means you might overfit a bit, right? If you really stick into the data a lot. Okay. Yeah, so and if it goes to infinity, then yeah, it's you don't tolerate any error, and then you go back to your hard margin. Yeah, so this is familiar just with that slack term. Now, just to tie it back to real life a bit, actually maybe support vector classifier. Okay, yeah, so this is our support vector machine. Support vector classifier and the ubiquitous scikit-learn. This is our C guy here that we're looking at here. Yeah, so regularization strength. This actually might be the inverse of, because saying the strength of the regularization is inversely proportional to C. So actually, they must have done like 1 over C or something, because in this case, the higher the C, the more, I guess, regularization. Hold on, wait. The strength of the regularization is inversely proportional to C. Is that right? So you increase C and you decrease. Actually, no. Sorry. This is the same C. Yeah. So if you increase your C, you decrease your regularization, which makes sense because you're penalizing your error more and you're turning into a hard classifier. So yeah, sorry, this should be the same. Yeah, the same C as this guy here. Yeah, cool. And this other stuff, how much of it do we see? Well, we see kernel a bit later. The other stuff you don't have to worry about, but yeah, kernel we'll see later when we look at the support vector machines when dealing with your non-linearity. Here, this guy here. So you can see here polynomial, RBF, yeah, hyperbolic. You can see it all here. So we'll talk about that a bit later, but this is tying it back to real life. So if you were to actually fit it as a support vector machine, you know what we're seeing. So this chap here is that C there, yeah. Yeah, cool. Yes, and then the final thing, soft margins, blah blah blah. Yeah, the final thing is your kernels and your non-linear guys, your non-linear support vector machines. Now, you notice that in all the examples so far, it's been a straight line or something linear, right? But obviously in real life, right? I mean, like there's plenty of data sets you can imagine that where the where it's not perfectly linearly separable, and maybe it's another shape. For example, here. Okay, here are some good examples. Now here, this is perfectly linearly separable data. Now, if you tried to fit a linear support vector machine here, you'd be stuffed. You're not gonna be able to do it, right? So then the question is, how? I want to use a support vector machine, but my data isn't linearly separable. Enter your kernel function, or before that, enter your feature mapping to a high dimensional space, and then your kernel function. Now that's our solution to this, effectively this problem. There we go. Yeah, but this is basically the same data set. You know, there's a cluster of one class in the middle, and then outside that circle, it's another class. Now, if I could find something that plots in 3D, that might be easier to see, but it's kind of hard to see there, isn't it? That's right. So, okay, so the solution to this problem here is we effectively map, you know, our feature space. So right now, see as 2D, we map it to a higher dimensional space. You know, it could be 3, 4, you know, with something higher, right? We map it to a higher dimensional space. And this mapping you can see here. So the new dimension 1 becomes x1 squared, the new dimension 2 becomes x2 squared, and then the last one's a blend of the two. Now the cool thing is, once we do this, it's kind of hard to see here, but just in 3D, once we convert this into 3 dimensions, we can actually draw a hyperplane that perfectly separates the data. So to deal with nonlinear data with your support vector machine, you need to find some sort of mapping which goes from here to here. Now, of course, like when you actually do it in practice, what will happen is that, you know, you would have a support vector machine, and you know, you'd actually test out a whole bunch of kernels. Now these kernels, I'll talk about it a bit later, but you can think of it as think of it right now as a feature mapping, and then a way to make the computation of that feature mapping easier, right? So there's quite a few. Let's find a few to show you what they look like. There we go. Yeah, so there's quite a few of them. Here we go. So this is from scikit-learn, and you can see here there's a few different, they show you a few different kernels which all, you know, look a little, these are linear, but then these look a bit different. So you can have a polynomial kernel which has a funny shape like this, or, you know, RBF, and there's other sorts of kernels around. But the idea is, you know, you'd maybe use cross-validation, or maybe use a training and validation. So you test out a bunch of them and see which one has the best, I guess, cost or error after, you know, you test them all, see which one is the best. So that's how you work out which shape, right? Which kernel function to use. Now, what I keep saying kernel, let's talk about what that is. Now, this in itself is not the kernel trick. This is simply a mapping from the R2 to R3. This is a mapping from a 2-dimensional space to a 3-dimensional space. Now, what is this kernel function nonsense? So you might recall that okay, here we go. Here's our Lagrangian. So when we're doing our support vector machine, right, all we care about, when we're doing our support vector machine, we're effectively using this guy here, the Lagrangian, to find the best separating hyperplane. We are trying to find, remember, that W vector, as well as that T, that line. We're trying to find that line which best separates the data. And to do that, we solve this Lagrangian. What do you notice? All we care about, why is this Z? Oh yeah, sorry, I'm skipping a step. So, here we go. Okay, so yeah, so here's a Lagrangian. So in terms of the data, all we care about is the dot product of the data points, of the features. Now, the kernel function effectively is this. So the kernel function, or maybe I did a slide, I forget. Here we go, I wrote something here. Yeah, okay. So let's say you have some mapping. How do I do this? Delete this guy. Okay. Let's say you have some mapping that goes from this feature space to this. Now, so phi, let's say phi. Is this phi or psi? No, it's phi, isn't it? Yeah, phi is a mapping from. I don't know, I'm just gonna make it. Let's call it real. How do I do that? Capital R. I don't know what the real. Is it real? Is that another LaTeX? I mean, okay, let's just pretend this is real. I forget what the LaTeX shortcut for real is, but let's say it goes from R to to R3. So this is your phi, which is the notation in the lecture notes, is that mapping function which goes from one to the other. Now, let's say the mapping function for this example is just this guy. Let's use this guy. This is our mapping function. It goes from here to here. Now, that's all well and good, right? But recall in our optimization problem, we don't actually we actually never need to directly calculate this. All we actually need is the dot product, right? So instead of having to transform everything, from R2 to R3 and then calculate this, if we have a kernel function, so what is a kernel function? So a kernel function effectively gives you the dot product of the transformation, right? Let me just move that here. So the kernel function gives you the dot product of the transform features. So this k xy is the same as this, okay? This saves us a step. So if we can find a kernel, so every mapping will have its own, I guess, kernel function, right? We'll have every mapping from one feature space to another. You can find, well, not every, but maybe if you can find a kernel function which is equivalent to some mapping, then that means you can just use that instead of having to transform the features into that feature space. We'll talk about it a bit more on that in our tutorial questions. Okay, cool. I think I should start with the tutorial questions now. Right. What is going on? Yes. Set. Okay. Back here. It's my shortcut. There it is. All right. Tutorial questions. Okay. So I think we already talked about question 1, so we're good. Yeah, question 2. This is a tricky one. Yeah, it's quite involved. Fortunately for us, a nice guy called Omar Gaddis has made this. So again, it's in the it's in here. So it's this guy here, extended solutions.pdf. Now, let me open up twice. I think it's better if I have the question on one side. There you go. Okay, right. So this is effectively going through by hand fitting of a support vector machine. Now, this is our data, and this is called the design matrix. And so each row is an observation. Observation 1, observation 2, observation 3, and these are our those are our predicted values. Right? Those are our sorry, I'm a bit thirsty. Those are our predicted values. Now they keep talking about this gram matrix. I don't think it's really necessary, but the gram matrix is effectively gives you the dot product of everything. So and obviously with the dot product you can calculate it. Just x, if you get a vector and then transpose it and multiply it, then you have the dot product, right? But what's happening here is that's a gram matrix. Yeah. So what the gram matrix is the ijth element is the dot product of I and j, right? So for example, this is a dot product of x1. This is x1 dot x1. What is x1? This guy. What's the dot product of 1 3 dot 1 3? 1 times 1 plus 3 times 3, 10. Similarly, this is a dot product of 2 1 dot 2 1. So 4 plus 1, 5, etc. etc. So this is what this is. Now, they only have it this way because it just makes it easier to find elements. I don't really think it's really needed for this example, but I mean that's what the dot product. I mean that's what the ground matrix is. So again, this is stepping through like fitting an SVM by hand manually. Now, you might recall that in order to solve this, we need that the Lagrangian, right? We need the Lagrangian. We need to find the stationary point of the Lagrangian. It's already given to us. Well, I mean, it's here. Huh? So this is what we care about. This is effectively the expression we want to maximize. Right? So, why do we bother setting up the ground matrix? It's not really necessary, but this gives us an easy way to find this because this is the dot product of two x's. Now, this gives us all the dot product of all x's. So, this ground matrix, you can use it for this guy here. Now, all we need to do now is plug the ground matrix into here, the y1, y2 into there, and well, we have to solve for the alphas effectively. The alphas are the weights for all the observations, and if they're not 0, then it's a support vector. So we plug. Oh, it's here, even better. Let me just zoom in a bit. Okay. I'm just gonna check if someone's asked a question. I haven't checked in a while, just in case. Again, so there's that. I think if you type something here, if you type something here, you can see it. No. Yes, if you type something here, I can see it. Perfect. Cool. So just a reminder, if you have questions, post it there. But otherwise, I am recording this, so I'm gonna find a way to upload it. Hopefully the recording doesn't stuff up. And again, feel free to record it on your side. I presume most of you guys using Mac OSs, so if you just go here, yeah, you should be able to see this. If you just go here, I hope you can see this. Then you go capture selected portion, and then you can record it. The only problem is it uses the microphone, so it's kind of like it'll record the speakers, talking with my voice. So it's just you lose a bit of quality, but I don't know. There's probably another way, but that's the easiest because it's already built into Mac OS. I mean, otherwise, feel free to record it your own way. Okay. Now you plug it into this equation here, and remember we're trying to solve for alphas, right? The alphas are the weights, and if the alphas are non-zero, then it means that it is a support vector. So we plug it in, and we have a constraint, which is that this guy here, and yeah, you just plug it in, and then remember. With the Lagrangian, we want to find the stationary points. In other words, we want to differentiate with respect to your alphas, which we're trying to solve for, mind you. We set it to 0, and then we set these guys to 0, and then you have a system of linear equations. So you have 2 linear equations and 2 unknowns, so we can solve it, right? So you used to your simultaneous equations. If you want, you can do your matrix, what's that thing called? Matrix inversion, where you solve for, where you can just do simultaneous equations or something to solve for that. And then, cool. And this is the definition, or this is what the weight vector is. The weight vector is, notice how it's made up of all the observations, right? And this gives us the weight. So what is this saying here? So this is saying here that our weight vector is made up of 1 of the first guy and half of the second guy, right? Which means that they are support vectors. Oh, sorry, let me say that again. Sorry. It's made a quarter of the first observation, 3/8 of the second observation, and -5/8 of the last observation. So they're all support vectors. Now obviously this is a toy example, but I'm just going to jump down here. Let me just pull this up over here. Now, see these three guys here? So that's like 1, 3, where's that? 1, 3, that's this guy. Actually, no, is it? No, sorry, this guy. This guy's 1, 3. This guy is 2, 1. So that's, I guess, this guy. And they're both positive, or blue. And this guy's 0, 1. 0, 1, that's this guy's negative, okay? So as it turns out here, they're all support vectors, and I hope you can see that. You know, like, so support vectors will lie on the edge of the road, right? Support vectors will lie on the edge of the road because, you know, you can imagine, right? If you're trying to maximize the side of the road, who cares who's behind the road? It doesn't matter. You could put whatever you want back here and it wouldn't affect the road at all, okay? So these are all support vectors, and we can see that here, that this weight vector, which is orthogonal to the middle of the road, or the median strip, or the lines, maybe you can think of, it's the weight vector, or the gradient, which is the gradient of this guy, is orthogonal to the gradient of this line, is orthogonal to the line itself, which is why it sticks out like that, and it's made up of these chaps here, and again the weights are here, okay? And if you add it all up, then you have the weight vector is, you know, 1.5. So, yeah, so 1.5 times your x1, x2 is equal to 3 on 2. So that gives us the equation of a straight line. So this w combined with the t, which then you solve, 3 on 2, gives you the equation of the straight line. And then you can use it to calculate the margin, which was defined, where was it defined? It was somewhere in the lecture notes. I'm trying to find it. Yeah, so this question is particularly involved. I understand it. It's a long one. It's one of these ones. Margin. There it is. Cool. Yeah. So the distance or the size of the margin is here. 1 on the norm of the Euclidean norm, mind you, of the weight vector. Cool. So that's question 2. Now let's talk about question 3. Okay. Did I write anything with question 3? I can't remember. I did. Cool. Right. Okay. So question 3. What's happening? Okay. So we are training a support vector machine. And there's 4 rows. There's 4 data points, right? And we fit it, and then we are told by the question that all of these are support vectors. So that means they're all on the curb, right? They're all on the, what do you call it? The side, the edge of the road, the curb, right? All these guys lie on, like, right on the edge of the road. They're on the margin. So recall that with a support vector machine, you can express the weight as just the support vectors, right? Because only the support vectors define the line, okay? In this case, all 4 of them define the line, the linearly separating line, and we are told that the weights are 1. They might not be 1, but to keep it simple, they are 1 in here. Now recall, in that previous example, which I need to find, where did I put it here? No. Here. Recall in this example here, the weights are 1.5. 1.5. Here the weights are 1, 1, 1. 1, 1, 1, 1, sorry. So there might not be 1, but it's just in this case they're 1. So the alpha is the weight of each of the observations. And again, if the weight is non-zero, it means that it is a support vector because it's helping define W. So remember, so this is W. You can think of it as, yeah. Okay. This is W really. W is made up of the support vectors. Okay. So what's happening here is that we've got our support vector classifier, and we want to perform classification on 2 new data points, on 2 unseen data points. How do we do this? So we just use this guy here, and so well, we just use this formula, don't we? So we go through each of these examples, and if it is a support vector, which all of them are, we just take the dot product and multiply it by the class and multiply it by the weight. So what did I write here? Yeah, so this guy here is the same as the weight. Okay, so for example here, what's happening here is that we are, well, there's the first one. So 17, how do we get to 17? So 17, what we do is we take the dot product of this first observation, and then we take the dot product of the first observation with this. Right, so we go 2 times 1, 2, and then it's nothing all the way up until the last 2. So 2 plus 12 plus 3. I'm missing something, aren't I? Wait a minute, that's not right. So 2 and then 14. Oh no, yeah, 17. Yeah, so 2 plus 12, 14 plus 3, 17. Cool. So 17 is the dot product of the first the dot product of the first support vector multiplied by a new observation, right? So that is this and this, multiplied by the weight, which we are told is 1, multiplied by the class, which is 1. Okay, so then, but then that's not the only support vector. We need to go through all 4. So then to that we have to add the second one, which is here. So then we need the dot product of this guy with this guy. So what is that? So 3 times 1, 3, and then plus 2 times 3. So that's 9, isn't it? So then there's 9, okay? And then we repeat it, and then we get 7 and 8, okay? But of course, this isn't 7 and 8 because these two are negative class. So it's really 17 plus 9 minus 7 and minus 8. So we get 11. So our prediction is positive. Now I repeat the same thing for this guy, and you get negative. So this is effectively using a support vector classifier. Now again, of course, when you do this in practice, you don't do it by hand. You get a scikit-learn to do all this stuff for you. You know, you instantiate this guy. You know, you instantiate this guy, and then you'd fit, I guess. Is this? Yeah. All right. Yeah, so like in new file. Yeah, so I guess in reality you just go, oh yeah, from sklearn.svm import support vector classifier, and then you instantiate it with whatever parameters, and then you go support vector classifier, and then you feed it to your data, with whatever settings you need, and then you can go, is it predict? It's predict, isn't it? Is the method predict? I'm pretty sure it's predict. Yeah, predict, and predict will give you a class, say 1 or 0 if it's binary. But otherwise, if you want the probability, you go predict proper. And then maybe you go predict on say x test, say something like that, right? But yeah, in practice you do something like this. And remember the C guy here. This is the regular the penalty for your soft margin, so you can make it whatever you like. But obviously in practice you do this, something like that. But of course, we're in uni, we want to learn the theory behind everything. Okay. Now, second last question. Kernel Trick. Now, I think question 4 is not worded very well. It's a little confusing as to what it wants you to do. It really isn't straightforward. But what it's asking you to do is they've basically given you a kernel function, right? So they've basically told you, no, not Victorian. Yeah. So they've basically told you that So they've told you that, wow, I'm gonna make this smaller. Okay. What do they tell you? Is equal to x dot. What's the latex shortcut for dot? I don't even know. I just click this. Oh, bullet. Oh, cool. Okay. There we go. And then you square all this, I suppose. I wish I had a whiteboard. A whiteboard would be easier, wouldn't it? There we go, cool. So this question is, they're basically, you know, given a kernel function, right? You know, what is the feature mapping? I think if the question, they should have written something like this, because it's a little confusing. I don't really explain what it is, but effectively you've got a back solve. There's some feature mapping. This. So there's some feature mapping which goes from actually we don't even know what. There's some feature mapping, right? Phi, which is this guy. We don't know what it is, but we know what the dot product is. We don't know what phi is, but we know what the dot product of two, you know, phi's applied to two different vectors is, and we want to back solve. So how do we do this? What you want to do is you want to crack this open, and then, you know, see if you can rearrange it and work out what it looks like. So the extended solutions give you a very good breakdown. Here it is. Yeah, here it is. Here. So you're given this kernel function, and it's equal to this guy there. So what you want to do is you want to crack this open, you know, and you realize, okay, cool. So this dot product is actually the same as this guy here. Now then the question is, given this guy here, can I copy this? I'm pretty sure I can't. No, that's not very good. So this dot product is this. Now we have to think, okay, like we have to work backwards. What kind of a dot product? We need a dot product that turns into this. Given that they have to be in the same form, right? You know, you can't have x1 squared in x1 and then y1 squared here because it's the same transformation. You know, phi makes you go from x1 x2 into this, but that same function phi makes you go from y1 y2 to this. So these two have to look the same. They have to be in the same form. So you have to think to yourself, okay, I have this guy here. Now how do I make a dot product that looks like this? Now I think if you just rearrange the terms, it should become fairly obvious, right? Like, I mean, you know, this, I mean, x1, this has to be all x1s, this has to be all y1s. So I mean, there's not really any other way to do it than to just put this one here, this one there. That's your first dimension, x1 squared. Similar story here. And then think of a way to combine this. You can't really make it from all the other ones, so you kind of just put it in its own little dimension. And of course, I have a 2 here, so, you know, you put a root 2, so when you multiply it together, it becomes a 2. So I hope this kind of makes sense, but I think the way to understand question 4 is, think of it like this. You're given a kernel function, you know, work backwards, and determine the feature mapping. The feature mapping for that kernel function. Okay, Cool. Let me check questions, no emails. Rightio. What's the last one? Oh, that's extra stuff. Okay, and then last one here is question 5. Okay, this example might look familiar actually because it is in lecture notes. That's a shortcut. Okay, whatever. No, it's in the second one, isn't it? Sorry, I'm just trying to find my slides. Here it is. Well, there it is. Okay, pull this out here, and then cool. All right, so this might look familiar. This is in one of the examples. Here it is. Cool. Now, what it's trying to do is it's trying to demonstrate to you why it is linearly separable, right? So here you can see it's not linearly separable, and the way that it does this is, I mean, it's not really a concrete proof, but it tries to show you, okay, look, if you plug, so you can imagine, like, see all these points here, right? I mean, they're close to the origin, aren't they? So if you just plug in a bunch of points in the origin, you can see here, it kind of maps to this little, well, it also maps to the origin, doesn't it? On this side, it maps to the origin. So if you just make up a few points, like say a -1, -1, I don't know, 1.5, -1, then you should see that when you map it over here, it's kind of clustered around there, and hopefully you can see that then the X class, it's all like above this hyperplane. So you just plug in like 5, 5, -10, -10, -100, -100. Negative, I don't know, 10, 10, and you should see it's all on that side. Cool. So I think that's all we have time for today. Let me know if you have any questions. Otherwise, I'm recording this. I hope that the recording goes okay. I'll upload it to YouTube or something. Otherwise, yeah, if on your end, feel free to record it. It's totally fine with me. Just a few things. I highly, if you are curious about machine learning and even statistics, I highly recommend this book, which I've uploaded into the Teams chat. It's very good, and it's, what else is there? Elements. This one has also been open sourced, and it's freely available. So I don't think I'm breaking any copyright by dumping it here. But yeah. Introduction and Elements. So I recommend Introduction. Elements is a bit more technical, but I mean, if you want a bit of a flavor behind this, I strongly recommend it. They're very good. I think there was also a question from someone in the forum about good textbooks. There's a couple I like. So obviously there's Introduction. What is it? No, it's called Hands on. Actually, I have it. Let me show you. Yeah, so this book here, I highly recommend it. I mean, again, it's been open sourced. I just printed it off because I think it's that good. I highly recommend this. Yeah, these two guys are legends. They're Stanford professors in statistics. I think that they actually have a bunch of video lectures based off one of these books. These guys, I highly recommend. I'm pretty sure Trevor Hasty R package. He wrote a bunch of cool R packages. Yeah. Yeah, the ElasticNet, that's right. Yeah, GLM. He did a bunch of ElasticNet stuff. GAM, Impute. Yeah, he's great. The other one I recommend is this guy here. I don't know if you can see it, but yeah, hands on machine learning with the scikit-learn and TensorFlow. I think this is a very good book as well. Probably the most. Oh, there's the wrong one. Probably the most. This one is. If you want something quite introductory, there's one I quite like. I think it's Sarah Guido, machine learning. Her book. Yeah, I've got this book as well. So this is a bit more introductory, a bit more basic. So if you want something easier, that's a bit of an easier read, I think this one's quite good. It's very organized. This hands-on machine learning is a little less organized. I don't think it's as but I think it's good as well. It's very good. And they've also got a new version which has Keras, I think. Well, which Keras is it's a deep learning, a popular deep learning package. I think it's maintained by, is it Facebook or who maintains Keras? Who maintains Keras? Or is it just completely open source? Because TensorFlow is maintained by Google, right? Yeah, look, I'm not sure. But anyways, yeah, so those are highly recommended books just for general curiosity. I'm not saying this in terms of the exams or in terms of this course and assessments, but just in general, if you are curious about this sort of stuff, yeah, Sarah Guido, Introduction to Machine Learning. I think they're quite good as well. And these two, of course, in Python. There's some other. There's R. This is Python. There's Python. But I mean, I wouldn't even consider this R resource. I would consider it more just it focuses on maybe the theory. I'd say more of rather than specifically any particular language. In terms of R, there's a bunch of other books I can recommend. But yeah, cool. So that's all we have time for today. Yeah, sorry about the delay in the beginning. I'll find a way to upload this recording later. But otherwise, just for the 10th, 100th time, all this stuff is here. Because I know you guys seem to, like seeing these quite quickly. So this probably makes it easier. All the content's there. This I probably need to re-upload because I've made changes, haven't I? But yeah, cool. Thanks for that. I will see you all next week at the same time. Stay safe. Stay at home. Let's all flatten the curve together. The best thing to do is stay at home, even though it's boring. Okay? See you guys. I think we'll flatten the curve.